Hello, I'm Lawrence Walsh. I'm the head of the School of Dentistry at the University of Queensland in Brisbane, Australia. I've been using lasers in my private clinical practice for about 20 years. What I'm going to be sharing with you today, very briefly, is some of the technique tips on using the Biolase diode laser. This is a really simple device that revolutionises clinical practice. In the tutorial, we're just going to talk about some of the ways that you can use the laser much more effectively on patients. It's really taking you back to dental school. It's not going to be that painful though, so sit back and enjoy it.
Welcome to this short presentation on understanding diode laser techniques. Now that you have a diode laser, you can start to appreciate how efficient this is as a cutting technology. You're probably familiar with electrosurgery, but you probably didn't realize that electrosurgery is a low efficiency method for cutting or ablating tissue. It requires high powers, upwards of 350 watts, to incise into tissue. A diode laser can ablate tissue at 100 times lower average powers at only a few watts. This massive difference in efficiency helps to explain why a modern diode laser can be handheld and battery powered and used in your practice as a replacement for many things that you previously would have done with electrosurgery. A key concept in understanding how the laser works is ablation threshold. This is the minimum amount of energy delivered into a given area that we need to ablate the target. We express this in terms of intensity, that is power density as well as energy density. If we are above this threshold, the target will be cut. If we are below the threshold, the material will not cut. Instead, it will warm up. We can use this warming effect of low intensities to great benefit to coagulate and thereby to control bleeding. The same differential effect of low versus high intensities is used in cavity prep erbium lasers to help achieve selective removal of resin restorations, calculus or caries from tooth structure. One of the most powerful examples of using selective ablation is when we work around metallic dental implant components. In this case, I'm exposing an implant located in the middle of a large skin graft which sits on a reconstructed mandible. The tissue around the implant has been selectively destroyed by the laser, but the implant abutment is unaffected. This principle of selective ablation is one of the most useful in laser dentistry. With an infrared diode laser, the beam is invisible, but we can see it using a conventional video or still camera. Because of their much wider spectral response, these devices see near infrared light extremely well. In the still image on the right, you can see how laser energy coming out of the tip is penetrating into the tissue. We can control how this penetration occurs by initiating the tip. Before we do that, let's spend a moment thinking about the size and shape of this invisible beam. You may think that the beam travels from the tip only in one forward direction, but in reality the beam spreads out in the shape of a cone with a divergence angle of about 9 degrees from the center, or 20 degrees altogether. Because of this divergence, the further away we are from the tissue, the less intense the beam. Here I have shone the beam onto a wall in a darkened room just to show how it spreads out. The size of the spot on the wall is similar to this roll of adhesive tape and the lid of this large jar. Knowing the distance from the tip to the wall, we can calculate the divergence of the beam. You don't need to do this. The answer is 20 degrees. The red targeting ring helps you understand how the distance from the target affects the size of the beam. As you can see, the laser beam, which is shown in blue, is contained just inside the red targeting ring. Now let's return to the process of initiating the tip. We can do this by wiping the tip across a cork or over carbon articulating paper. The purpose of initiation is to change the pattern of energy emission. In simple terms, it constrains the laser energy in space. The material coated onto the end of the tip from the cork or carbon paper becomes very hot when the laser is used. We can use the same method to coat the side of the tip for doing an external bevel cut during a gingivectomy. If we don't initiate the tip, the laser energy will go further into the tissues and we will get more collateral damage. This histological slide of a laser cut sample of soft tissue shows this damage on the side of the incision. I've drawn a small dotted line to show the outline of the affected tissue. The schematic on the upper right hand side shows the relative penetration. With the initiated tip, we will get a more selective and superficial effect from the laser, the yellow bar, for shallow penetration. If we haven't initiated enough, the result is the longer grey bar, and if there is no initiation, the energy will go furthest, the red bar, and we won't get cutting. Initiating tip is not difficult to do, and there is a nice guide for this on the Biolase website. You can practice with articulating paper or cork, or even thermally printed labels or supermarket receipts. Cork is probably the easiest to start with for most procedures where you want to initiate the end. Articulating paper is best for initiating the sides for several millimeters, for beveling. Interestingly, one of the most common reasons for service calls for diode lasers is because the user has forgotten to initiate the tip and then tried to cut. All that happens is heating of the surrounding tissue without effective ablation. Now let's think about which tip to select. Tips come in different lengths as well as in different sizes. Because of the inverse square law, changing to a 200 micron tip from a 400 micron tip halves the diameter of the laser spot and concentrates the beam, so it increases the power density by a factor of 4. When we change to a larger tip, the reverse is true. We spread the energy out in a greater space. This means you get similar power densities on tissues from lower power settings by using smaller tips. Always use smaller tips for soft tissue cutting. Keep the bigger tips for when you don't want to cut tissue, such as when troughing around a crown prep to get hemostasis, or for perio-disinfection. Another key aspect of using a diode laser well is the clinical technique. For surgery, you should use a light brushing action, barely touching the tissue surface. This technique used with an initiated tip is how we cut tissue. The small or zero distance from the tip to the surface gives us our greatest intensity. When we want to coagulate, we should be away from contact with the tissue, so that the beam spreads out or defocuses. This lowers the intensity below the ablation threshold, so we get localized heating and coagulation rather than ablation. Let's now look more carefully at the types of thermal effects on tissue caused by laser treatment. We can see these effects by observing how the tissue responds to laser energy. The trend of effects caused by heat is the same as those for electrosurgery, so let's use this simple graph of what happens as we move to higher and higher temperatures. Let's begin at the lower temperatures. We don't want to see a lot of coagulation during surgery. You can see white areas on the lower left clinical slide during the laser frenotomy, caused by using too large a tip diameter, not enough power, and not enough initiation. As the temperature scale rises, the tissue proteins become quite sticky. We will need to remove tissue debris from the tip by gently wiping it. At this stage, the tissue begins to shrink. At 100 degrees Celsius, water boils, so the water in cells will boil and we will get vaporization. The wound will have a yellow-brown edge, just like the gingivectomy shown on the upper left. This sun-tanned looking surface is what we want to see, all brown and very little white or black. Above 100 degrees, as the dry tissue components burn, we will get carbonization, and the area will start to look black from the carbon, just like the gingivoplasty on the upper right central incisor in the top middle image. Once there is a lot of carbon, the speed of cutting goes down, and all we do now is heat the carbon and damage the tissue. When using the diode laser for surgery, use short strokes and keep the tip moving constantly. Don't spend too much time in one place or you'll get collateral injury. First is coagulation, which looks white, and if you stay still long enough, black from charring and carbonization. So look at what the laser is doing to the target and keep your speed to around 1 millimeter per second. At the end of the surgery, the tissue should still look moist. and the laser cut surface should look brown, like it has a great suntan. As we are using the tip during surgery, its performance becomes affected by heat-induced degradation. This is why the tips are designed as disposable items for single procedure use. A damaged tip will show a bizarre pattern from the red aiming beam. During contact procedures like surgery and perio-disinfection, sticky strands of tissue will coat onto the sides of the tip and onto the end. This material needs to be wiped off so the emission of laser energy is not affected. At the end of the procedure, just throw the tips away. Don't try to steam sterilize them or they'll just melt. Let's talk now about why less is best. Less pulse duration. With a diode laser we can select a pulsed mode. A shorter pulse followed by a longer delay means there is more chance for the target tissue to cool down between laser pulses because of tissue blood flow. We can enhance this by using cooling water spray between bursts of laser pulses. Less procedure time. Using a higher power with pulsed modes means that we will be above the ablation threshold, so every pulse will cause cutting. We can do procedures quicker at higher powers. A smaller tip. A smaller tip puts the laser energy into a smaller space, which is like focusing a magnifying glass to get the sun to start a fire. More laser energy in one place means we are above the ablation threshold, so once again every pulse will cause cutting. These three factors combined together mean a faster procedure and less collateral injury, so less post-op problems. When we come to using the diode laser in a periodontal pocket, a gentle stroking action is essential. Some articles in journals suggest putting the tip right down to the base of the pocket and sweeping it sideways many times before withdrawing it, as shown on the left diagram. This method increases the chance of blood or crevicular epithelium interacting with the end of the tip and reducing its output. A better method is shown on the right. This is a U-shaped action which begins by inserting the fibre and then lasing in one action as the fibre is moved sideways and withdrawn, like a backwards letter J, to complete the U. By doing many of these U-shaped movements, you can more easily check that the end of the fibre remains clean. The end of the fibre can be wiped clean with a small piece of gauze or a small disposable sponge designed for cleaning dental instruments during their use, just like the one shown here. If you want to add a liquid to this sponge, then 1.5% hydrogen peroxide or sterile saline would be the best for helping to clean the tip. Let's look now at how we control bleeding in unusual cases. In most procedures we will see a yellow-brown cut surface with hardly any carbon and which won't bleed, just like the gingivectomy shown on the left or the gingivoplasty on the right. The 940 nanometer wavelength absorbs very well in hemoglobin as well as in water, so it will seal small blood vessels as it cuts. In situations where the tissues are very inflamed and more vascular, we need to get more heating to give us greater coagulation. We can do this by using longer pulses or continuous mode, and at the same time pulling the tip away from the surface to spread the beam out. As shown in this simple cartoon, a short pulse has a limited action on adjacent tissues, but a longer pulse or continuous mode gives greater collateral heating. Here's a case where we needed to do just that. An elderly patient with a mandibular overdenture and many problems in the few lower teeth that were supporting this. The patient has a severe coagulation disorder, and, for added complexity, there is an aberrant arteriole running between the two central incisors in the area shown in the oval highlight. The pre-op situation is shown on the upper left. This arteriole was uncovered during the gingivectomy, which made the appointment even more exciting. I applied compression to the area and then lased directly into the end of the bleeder using continuous wave in defocus mode, staying quite still to accumulate heat into the vessel's cut end. I then lased the ooze of blood. By doing this for several seconds, a lot of carbon built up, which was heated by the laser, adding to the overall effect. It basically becomes a small hot coal. In the 1-week post-op review, shown in the lower right, you can see how well all the tissues have healed, except the area where I used the laser to create that intentional heat damage. Hopefully you will never need to use this technique tip in your practice, but it's good to have in your pocket nonetheless. Let's now summarize some of the key points we have learnt and compare the diode laser to electrosurgery. Both use a gentle stroking action to touch the tissue, but only the laser can be used in non-contact mode. With electrosurgery, we change the wave shape to move from cutting to coagulation. With the laser, we can reduce the power, increase the distance, increase the pulse duration, and increase the exposure time to do this same switch. We have more technique options available to us. With electrosurgery, we change the electrode tip size and shape. With the laser, we change tip size, the pattern of initiation, and the distance from the target. It's so easy to just change the distance a little to control the laser's effect. With electrosurgery, the collateral injury is deep in the tissue and hard to see. With the laser, we see what is happening on the surface and use that information to guide us. With electrosurgery, charring and carbon increases impedance and slows down cutting. With the laser, charring and carbon absorb laser energy, and they also slow down cutting. They become hot, our special trick for handling bleeders. With electrosurgery, the impedance changes between different types of tissue, and we can't gauge that difference. With the laser, the hemoglobin and water differs only slightly between tissues, and we can see that because tissues with more hemoglobin have a deeper red color. With electrosurgery, we need lots of different shaped tips. With the laser, we can use a simple tip and just change how we initiate it. We can shape the tissue by delivering more energy in one place versus another. It's just like sculpting.
Thanks for visiting with us. I hope these tips from down under put you on top of the diode laser game.